Good day. Today we're going to continue our discussion regarding neutral geometry. In this case, we are going to discuss the equivalence of parallel postulates. There are many ways that we can state the parallel postulates. We might say um, through a point, exactly one parallel line. We could also say parallel lines never met or never meet. And then we could also say that the angle sum of a triangle is equal to 180 degrees. These are all correct. Now, we are going to explore, okay, okay how these statements, okay, and the other statements are equivalent. So, when we are talking about equivalent, it means to say that we have here the symbol. So you have a double head B, meaning that um, statement A is equivalent to statement B. This further means that if we assume A, then we can prove B. Or and at the same time, if we assume if we assume B, we can prove A. So, meaning they are logically interchangeable. So, this equivalence has implications. One of which is any one of these statements characterizes Euclidean geometry. And then um, they all separate Euclidean from hyperbolic geometry. And then in neutral geometry, we can also prove none of them. And if we add w- any one to neutral geometry, we can prove all the others. So in this discussion, we will look at several equivalent forms. What are those equivalent forms? We have the Hilbert's parallel postulate, the uh, Euclid's fifth postulate. You have the angle sum, which is equal to 180 degrees, the existence of the rectangles, the uniqueness of perpendiculars, and all other equivalents. Okay, so let's have the logical equivalence. So when we are talking about logical equivalence, so you have here two statements P and Q are logically equivalent, written as this one. You have P double-headed arrow Q in a given axiomatic system if P implies Q, meaning if P is true, then Q also is true. And Q implies P. If Q is true, then P is true. Okay, so in other words, adding P to the actions allows you to prove Q and vice versa. So when we are talking about logical equivalence, uh, it is a powerful concept. It means that two statements are interchangeable. They have the same logical content, even if they look different. Okay. So in our context, statements are equivalent in neutral geometry if using axiom 1 to 4 of Hilbert, okay, plus the statement P, we can prove statement Q. Okay, we have using axioms 1 to 4 plus a statement Q, we can prove statement P. So, example for that, we have the angle sum is equal to 180 degrees. Okay, um, double implications, rectangle exists. Okay, another, we have here, this means if we can prove triangle have the sum of 180 degrees, we can prove rectangle exists. Conversely, if we know rectangle exists, we can prove angle sums equal to 180 degrees. Okay, so again, Um, Somehow, this logical equivalence is the transitivity. Okay, this means that we can prove the whole chain of equivalences. For example, we have the Hilbert's parallel postulates. Um, Double implies Euclid's parallel postulates, which also double implies angle sum of the triangles equal to 180 degrees, which also double implies um, rectangle exists, and so on. So when we say statements are equivalent in neutral geometry, we mean that we start with the uh, axioms 1 to 4 of Hilbert. Take note that the Hilbert's axiom 1 to 4, they are neutral geometry, meaning we don't use the parallel postulates. And then adding any one of the equivalent statements, this gives us the same theory. Okay, meaning that if we are going to add parallel postulates, we can now um, describe or prove the Euclidean geometry. Okay, so without any of them, we have neutral geometry. With any one of them, we have the Euclidean geometry. Okay, so we have here forms of parallel postulates. So we have here Hilbert's parallel postulates. Uh, Here, for every line L and every point P not on L, there exists at most one line through P that does not intersect L. So this is the Hilbert's parallel postulate, meaning, not meaning, notice that uh, there is a term there at most. Okay, so notice the careful wording at most one. Okay, so combined with the uh, corollary 2 from 4.2, okay, diba? At least one parallel exists. This gives us exactly one. Okay, so take note the at least one parallel that is proven in um, neutral geometry plus at most one parallel of the Hilbert's axiom uh, exists. There is now exactly one parallel in the Euclidean geometry. Another, we have the Euclid's fifth postulate according to the wordings of Playfair's axiom. So we have here that every line L and every point P not on L, there exists exactly one line through P parallel to L. Okay, so this is the most common modern formulation. Okay, the Playfair's axiom in the his interpretation to the Euclid's fifth postulate. So it's exactly one directly. So John Playfair rephrased Euclid's awkward statement into this clearer form. Another, you have the Euclid's fifth postulate, which is the original form. So we have there, if two lines are cut by a transversal such that the sum of the interior angles on one side is less than 180 degrees, then the two lines meet on that side. Okay, so we have here now, if interior angles on one side sum to less than 180 degrees, the lines meet on that side. So in other words, if these interior angles sum to less than 180 degrees, Euclid says that lines will eventually meet if extended. Okay, another, we have here the angle sum statement. The sum of angles in every triangle equals to 180 degrees. Okay, so this is the most intuitive. Okay, because every triangle has the sum of 180 degrees. We've seen this cannot be proven in neutral geometry because according to the Shakeri Legendre, okay, only gives less than or equal to 180 degrees. Okay. Another rectangle existence, there exists a quadrilateral with four right angles. So a rectangle is a quadrilateral rather with four right angles. In hyperbolic geometry, this doesn't exist. Okay, the existence of even one rectangle is enough to characterize Euclidean geometry. So all five of these are equivalent. Okay, they are equivalent. The Hilbert's parallel postulate, the play first axiom, the Euclid's fifth postulate, the angle sum statement, and then the rectangle existence. These are all equivalent. So if we assume any one, we can prove all the others. Okay, that's what we mean by equivalent form of the parallel postulates. Okay, so take note, mathematicians spend centuries trying to prove one of these from the other axioms. Now, we know they're all independent. So you can prove them without assuming at least one of them. So or not just one of them, something equivalent. Okay. So meaning if we assume that one of the statement is true, we can now prove all the others, okay, to be true also. Okay. So we have here Hilbert's the equivalence of the Hilbert to Euclid's fifth postulate. Okay. So theorem 4.5 in neutral geometry, Euclid's fifth postulate is equivalent to Hilbert's parallel postulates. Okay. So again, you have the Euclid's fifth to double implication to Hilbert's parallel postulate. Okay. Now, this theorem shows that Euclid's modern formulation and Euclid's ancient formulation are actually the same thing. Uh, they're just said differently. Okay. So, okay. So we have our outline. So we must prove two implications. Hilbert's parallel postulate implies Euclid's fifth. Okay. If at most one parallel exists, then lines with interior angles less than 180 degrees must meet. And then Euclid's fifth postulate to implies Hilbert's parallel postulate. So we have if lines meet with interior angles less than 180 degrees, then at most one parallel can exist through a point. Okay. So for the what we call this one, for number one, Hilbert's parallel postulates implies Euclid's fifth postulate. Um, we have to assume that we have to assume Hilbert's parallel postulate. So at most one parallel, and then we can prove um, Euclid's fifth. Okay, in the Euclid's fifth, if interior angles is less than 180 degrees, lines meet. Okay, now to have our what I call this one proof. Okay, our strategy for this one is that we can suppose interior angles sum to 180 degrees. Then if the lines don't meet, they're parallel. But if we can construct another line through P parallel to L using angle properties, okay, this gives two parallel lines contradicting Hilbert's parallel postulate. So therefore, lines must meet. For the second one, you have the Euclid's fifth, okay, implies Hilbert's parallel postulate. Okay, our what do you call this one? Our strategy is that we suppose two lines, let's say M and N through P, are both parallel to line L. So consider the transversal through P. The interior angles with M and N are different. So at least one pair of interior angles sum to less than 180 degrees. Now, by Euclid's fifth postulate that line must meet L, that, that would be contradiction. So at most one parallel. So we won't we won't go through the detailed what do you call this one two column proof, but the main ideas here as are The uniqueness of parallels relates to when line meet, and then both formulations captures the same geometric facts, and then we can translate between them. Okay. Okay. So here is the proof that Hilbert's parallel postulates implies Euclid's fifth. Okay. So we have here the step one: assume Hilbert's parallel postulate at most one parallel through P to line L. Okay. That would be our given of what we are assuming. So in step one, which is the assumption, we're assuming that Hilbert's parallel postulate, and then we can see that this would be our starting point. Okay, so step two, suppose lines M and L prime are cut by transversal T with interior angles summing to less than 180 degrees on one side. So this is the hypothesis of Euclid's fifth. And then let angle 1 plus angle 2 less than 180 degrees, where angle 1 and angle 2 are interior angles on the same side. So that's from our step 2. So now we take an arbitrary configuration satisfying the hypothesis of Euclid's fifth in this step 2 and step 3. Now we can see here that two lines M and L prime cut by transversal T, and then the interior angles on one side sum to less than 180 degrees. So we want to show that M and L prime meet on that side. Okay. Step 4, then angle 1 plus angle 2 greater than 180 degrees, where angle 3 is on opposite side of T from angle 2. So angle 2 and angle 3 are supplementary. So angle 2 plus angle 3 equals 180 degrees. Okay. So the angle on opposite sides on the transversal are supplementary, which forms linear pair. So if angles on one side sum to less than 180 degrees, angles on the other side sum to greater than 180 degrees. So we have here construct ray from P, making angles with M that sum to exactly 180 degrees on the other side, or on one side. So that's our axiom, the angle construction. And then this ray is parallel to L. Okay, let's call this one as uh, N. So by theorem 4.1, the converse direction would use Euclid's fifth, but we construct it differently. Okay. Now, technically, this is a clever. We construct a line N through P that makes the angle with the transversal uh, summing to exactly 180 degrees. So in our earlier theorem, this makes N parallel to L. So actually, this construction is subtle. Okay. Um, the fact that we can construct angles in any measure, that is theorem 4.3, property 4. Okay. So that's our contention. So we have here, since angle 1 plus angle 2 is less than 180 degrees, line L prime is not this parallel N. So that's different angles means different lines. Okay. Now, take note here that line L prime makes angle summing to less than 180 degrees. That is on step 3. Now, line N makes angle summing to 180 degrees. That is on step 6. Therefore, line L prime and line N are not the same. So they are different angles, means different lines. And then on step 8, by Hilbert's parallel postulates, there is at most one parallel through P. That's for our assumption of step 1. So Hilbert's parallel postulate says that at most one parallel line through P to L. Okay. So we constructed one parallel. Therefore, any other line through P must meet L. Therefore, uh, L prime must meet M. They are not parallel. That is from step 7 and step 8, that L prime is not equal to line N. So L prime meet L. So this is our conclusion. Since L prime is not the unique parallel N, it must meet L. So this is exactly what Euclid's fifth says. Okay, so we have now one direction, okay, or direction one. So the key is constructing the unique parallel explicitly, then showing any line with different angles must meet in the original line. Okay, so more equivalent statements. So we have here other statement equivalent to parallel postulate. So we have proposition 4.7, Hilbert's parallel postulates um, is equivalent to the statement if L intersects one of the two parallel lines, it intersects the another. Okay, so this is technically transitivity of intersection. So if two lines, let's say M and N, are parallel, and a third line T intersects M, then T must also intersect N. Okay, so in in Euclidean geometry, this is obviously true. However, in the hyperbolic geometry, this is false. So T could be a parallel to both M and N. Okay, so this statement characterizes Euclidean geometry. Another, we have proposition 4.8, Hilbert's parallel postulate is equivalent to the converse to theorem 4.1, parallel lines have congruent alternate interior angles. Okay, so recall theorem 4.1. So if alternate interior angles are congruent, then lines are parallel. So the converse, if lines are parallel, then alternate interior angles are congruent. So we prove one direction in neutral geometry. So the converse requires parallel postulate. So take note that in neutral geometry, the alternate interior angles are equivalent implies parallel lines in what we call this one Euclidean geometry. We have, if they are parallel lines, then the alternate interior angles are also congruent. Okay, let's have the proposition 4.9. Hilbert's parallel postulate is equivalent to if T is a transversal to L and M, with M parallel to L and T perpendicular to L rather, then T perpendicular to M. Okay, so this is the perpendicular transversal. So if a transversal is perpendicular to one of the two parallel lines, it's perpendicular to the other. Okay, so this is obviously true in Euclidean geometry, but not provable without the parallel postulate. Okay, so proposition 4.10, Hilbert's parallel postulates is equivalent to if L parallel to M, perpendicular T, and T perpendicular N, then either L parallel to N or equal to N. Okay. Um, this is a perpendicular relationship. So this is about relationships between perpendicular and parallel lines. So it says perpendicularity is transitive with respect to parallelism in a certain sense. Okay. Proposition 4.11, Hilbert's parallel postulates equivalent to angle sum of every triangle is 180 degrees. So this is angle sum. The angle sum of every triangle is equal to 180 degrees. This is perhaps the most intuitive equivalent because we've seen in the Sakari legendary, which proves that the angle sum is less than or equal to 180 degrees, that is on the neutral geometry. We cannot prove the angle sum greater than or equal to 180 degrees without parallel postulates. So the equality characterizes Euclidean geometry. Okay, so all these, what do you call this one? So, and many more. So, existence similar triangles, Pythagorean theorems, existence of rectangles, and so on. Okay, so take note that all these statements are equivalent. They form a web of connections, like uh, Hilbert's parallel postulates, equivalent to Euclid's fifth, and then this is the Euclid's fifth is equivalent to angle sum, which is equal to 180 degrees, which is also equivalent to rectangle's existence, which is equivalent to 4.7, proposition 4.7 to 4.11, okay, something like that. If you assume any one, you can prove all of the others. Okay, so why so many equivalent forms? So the deep structure of Euclidean geometry, all these equivalence forms reveal the same underlying truth about Euclidean space. It has zero curvature. Okay. So the parallel postulate is really about curvature of space. Okay. So in Euclidean geometry, flat space, zero curvature. Okay. So flat space, we have to take note that in Euclidean geometry, we are talking about flat surface, meaning exactly one parallel. So the angle sum is equal to 180 degrees. Now, in hyperbolic geometry, there is a negative curvature. Okay, the saddle shape or the bowl shape. Okay, so negative curve in the hyperbolic geometry. So infinitely many parallels, and then the angle sum is less than 180 degrees. And then in spherical geometry, there is a positive curvature. There's a sphere shape. Okay. So meaning no parallel lines, and then the angle sum is greater than 180 degrees. Okay. So what this means, the parallel postulate isn't arbitrary. It's the defining feature of the flat surface or flat space. Okay. So all the equivalent forms are different ways of detecting whether the space is flat. Okay. So what do you call this one? Um, rectangle exists only possible in flat space. So the angle sum is equal to 180 degrees. That's the characteristic of a flat triangle. And then exactly one parallel, that's the property of flat planes. And then the Pythagorean theorem exists, okay, only exact in flat space. So they're all saying space is flat in different ways. Okay. So here, all these equivalent forms prove different aspects of flatness. Denying the parallel postulate gives us curved surfaces or curved spaces. And the neutral geometry is the core shared of all geometries. So historical impact, the discovery that all these forms are equivalent yet unprovable from other axioms was crucial to the development of non-Euclidean geometry in the 19th century. So, for 2000 years, okay, 2000 plus years, mathematicians tried to prove parallel postulate from the other axioms. However, they keep finding equivalent statements thinking maybe this one is easier to prove, but they're all equivalent. So none can be easier than the others. They are all equivalently unprovable. So this led to a realization that the parallel postulate is independent. It can't be proven or disproven from the other axioms. So we have Gauss, Lobachevsky, Bolyai, okay, in 1820th, 1820 to 1830, that where these mathematicians independently realized, okay, that we can deny the parallel postulate to get a consistent geometry in the hyperbolic, where all these equivalent statements are false. So this is revolutionary. It shows geometry could be different from Euclid's. So here is now our contention. So if you can remember with our first questions when in our first meeting, what makes modern geometry modern? Okay, if this concept exists even before even the last 2000 plus years. Now, here is our answer. Modern geometry gives us modern perspective. So we can understand that we have neutral geometry, which is the core in the, um, what do you call this one? In the world of geometry. If we have the parallel postulate, we chooses which geometry. Okay, uh, Euclidean versus hyperbolic. And then the equivalent forms, meaning different manifestation of the same choice. Okay. So summary and looking ahead, here would be our takeaways. Many geometric statements are equivalent to the parallel postulate. Hilbert's parallel postulate uh, equivalent to Euclid's fifth, which is equivalent to angle sum 100 equal to 180 degrees, which is equivalent to rectangle axis, and so on. So all these forms characterizes Euclidean or flat geometry, and they're all unprovable in neutral geometry. They're all false in the hyperbolic geometry, and this existence reveals the deep structure of geometric systems. And then what would be the big picture? The neutral geometry, the axiom 1 to 4, plus any equivalent form of parallel postulate would be the Euclidean geometry. Okay? So again, um, we've seen that parallel postulates have or has many phases, but they are all the same underneath. Okay, the parallel postulate isn't just one statement. It's an entire class of equivalent statements. So mathematicians over the centuries keep discovering new forms, but they are all equivalent. So this means in Euclidean geometry, you can use any of these equivalent forms freely. So need to prove something about angle sum, use the parallel postulate. So if you are going to construct parallel, use the play first axiom. So if you need the properties of rectangle, then use their existence. They're all available once you assume any one of them. Okay. So I hope you get something out of this discussion, and thank you very much for listening.